In the previous section, we looked at matrix transformations. We saw that that's a particular type of linear transformation. In this section, we're going to look at and introduce linear transformations more generally. So let's first make sure we get a definition down. So let's let V and W be vector spaces. So that means V could be Rn, for example. Rn is a vector space, or a subspace of Rn, because all vector subspaces are vector spaces, but it's also a subset of another vector space. Okay, so we have two vector spaces. What we're going to do is we're going to define a function from one to the other. Let T be a function from V to W. Okay, we call a function that maps from one vector space to another vector space, we call it a transformation. But this particular transformation will have two important properties, such that for any vectors u and v in vector space V, and any scalar k, we have T of a scalar multiple of vector V is equal to scalar multiple times the transformation on V. And also the transformation of the sum of the two vectors u and v is equal to the sum of the transformations of u and v. Okay, in this case, we call T a linear transformation if it has these two properties. All right. So in summary, what are we doing here? What we're saying is that if we have a linear transformation, it doesn't matter if we scalar multiply a vector before the transformation or after the transformation. Okay, it doesn't matter if we add two vectors together before we transform them or after we transform them. And these two properties lead to a really important result. And we saw this with matrix transformations, but it's generally true for all linear transformations. Note, linear transformations preserve linear combinations. And that is an incredible aspect of linear transformations. It's why we like these two properties, because with these two properties, we are able to preserve linear combinations. So let's let T from a vector space V to a vector space W be a linear transformation. Let V1, V2, all the way to Vk be vectors in my domain V. And let A1, A2 to AK be scalars. Doesn't matter which scalars. Let's set vector U to equal to the linear combination of vectors V with coefficients A1, A2, and so on. Okay, so we just have a linear combination here. then if we take the transformation of u, that means we're taking the transformation of the linear combination. And by my two properties, if I take the transformation of a sum, it doesn't matter if I apply the sum before I take the transformation or take the transformation of each individual vector and apply the sum after. Okay, so here it works with 2, but it actually applies for any number, because I could say I'm going to take this as my first vector and all of this is my second vector. So transformation of a1 v1 plus transformation of everything else. And you could see if I keep on doing this, now I could do the same thing here. I could say transformation of this and then the transformation of everything else and split it into two transformations. If I keep on doing this, I could get a transformation of the sum of all these individual terms. Okay, and then we have the transformation of all these terms, but they're scalar multiples of a vector. And by one of the properties of a linear transformation, we can either apply the scalar before, but that's the same as multiplying by the scalar after we take the transformation of a vector. So in a way, I could pull it out of the inside of the transformation. So I get a1t v1 plus, pull the scalar out here, a2t v2 plus dot 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 plus akt vk. All right, and we could see here what I mean by preserving a linear transformation. U was a linear transformation of the vectors in V. The transformation of U we can now see as a linear combination of the transformation of the vectors V. What's more, I expressed U using coefficients A1, A2, AK, right? Those were the coefficients of the linear transformation. The coefficients of the linear transformation TU could be also A1, A2 to AK. It has the same coefficients.